Good afternoon, everybody. Welcome to a Ski Institute Distinguished Lecture. And today we are happy to have Ronny Ramlau from the Johannes Radon Institute for Computational Applied Mathematics, RICAM. He's from Austria in Linz. He's the scientific director there and has been doing work in inverse and imaging problems for a number of years, which is definitely a topic of interest here at the Ski Institute. So we learned that he was doing a sabbatical in the US, and we had a connection with Frank Stenger, who knew Ronny well, and so we were able to convince Ronny to come over and spend a little bit of time with us and give a distinguished lecture. So please join me in welcoming Ronny Ramlau for a distinguished lecture.
You hear me? Yeah, perfect. Yeah, good. Thanks for having me here. And I mean, some of you know that I spent a year in Salt Lake, and it's always nice to come back and see how it actually developed and see the mountains. And of course, I would have liked to ski up there, but it's not. Well, I don't know. If there would have been snow, I'm not really sure I would be here now and give the talk, or if I would be up there. So it's maybe good that there is no snow. Yeah. So that's, you see there lots of affiliations. So the first one is RICAM, which is actually, I should say, it's my second one. So the first one would be the Industrial Mathematics Institute at the Kepler University. So RICAM is, I'll go into that a little bit later, is a research institute also located in Linz, which belongs to the Austrian Academy of Science. And so my chair, my group is in the Industrial Mathematics Institute. So at RICAM, as Chris said, I'm scientific director. This is nothing really important. It just meant that I was not really fast enough to get away to have this job. So because it's a lot of administration that you have to do in this kind of job, and it actually steals your time for research, which is not a good thing. And that's one reason why I enjoy being in Ohio, being in the US, because I can just say, well, there's 6 hours time difference. Don't bother me with that stuff. So that's a good thing. Okay, about 7 years ago, I think, we didn't know anything about. We didn't even know what adaptive optics mean. We didn't even know that there exists or there will be existing some extremely large telescopes. So we had no idea about the topic that I'm presenting to you yet. Of course, we knew a lot about inverse problems. So this is joint work with a lot of people that work in particular in this adaptive optics stuff, doing development of mathematics and algorithms for these kind of things. Let me see if that works. Not yet. Now it works. Okay, so short overview. I will actually talk first a little bit about what is adaptive optics, what is behind this, what is the techniques, why do we need it, and then I will go to so this whole thing of adaptive optics needs. Well, when you do adaptive optics, you need to solve several inverse problems, and I just want to walk you through these problems a little bit. So, and that starts with wavefront reconstruction. So you have incoming waves, you would like to reconstruct the wavefronts of the incoming waves. It's also related to this single conjugate adaptive optics system. Then I will talk a little bit about atmospheric tomography. So this is as close as I come in my talk to medical imaging. Of course, we're still doing medical imaging, but not in this talk. So I'll talk about the systems and the models that actually are behind atmospheric tomography, and I will talk a little bit. So this is where actually, well, if you're not that much interested in mathematics, you actually can plan here a little nap. So that will be the analysis of the periodized atmospheric tomography. There will be some formulas there, okay? And then I will talk about how do we actually reconstruct for atmospheric tomography. How do we reconstruct turbulences in the atmosphere? And I will not talk about Catchmarch reconstructor, and I will not talk about the approximate inverse for atmospheric tomography. However, I will talk a little bit about a wavelet-based two-step methods. And at the end, I will talk a bit about how the correction is done in the end, and then some further problems and further topics that we are doing in, let's say, the area of mathematics for astronomy. Okay, so what is it about? This is cooperation with ESO. ESO is the European Southern Observatory. So it's not in the south, well, it is in the south, but in the south of the organization, at least in the south of Germany. It's located in Munich, but they run actually telescopes in the southern hemisphere in Chile. So there's this Atacama Desert up here, and on top of the mountains there in the desert, they already run the so-called Very Large Telescope, or short VLT. That's 4 telescopes. Each of these telescopes has a mirror, a primary mirror of 8 meters, and they can actually connect these 4 mirrors and get a huge image there. This is about an 2,500 meters height. What I try to, it's about, yeah, so like the base of Alta. So that's, if you go to Alta, so then that's where these telescopes would be built. So the air is quite dry up there, so it's beautiful sky, no clouds up there, so that's why they actually choose this place. Yeah, so what they want to do is they want to build the so-called European Extremely Large Telescope, that is the E-ELT. When we started our project, it actually had one mirror with a diameter of 42 meters, and it was projected to cost about 1 billion euro. So then they couldn't actually decide when to start, and time went on. Money actually was worth less, but still we only had 1 billion euro. So nowadays we just can buy a 39-meter telescope. So, but still it will be the largest telescope on Earth. Just as a side note, originally they wanted to build the so-called OWL, the overwhelmingly large telescope, with a diameter of 100 meters. But they realized actually no way they could actually, with today's techniques, they couldn't build it. It's simply from the mechanical point of view, from the computer science point of view, it was not possible to control this kind of telescope. So, of course, I always talk about the E-ELT. I always have to say when I'm in the States, there's, of course, another telescope maybe going to be built from California's institutes. I think Caltech is involved, and I think others too. Canada is involved, and some Chinese universities are involved. That's the so-called TMT. They're not actually better with their acronyms, so it's a 30-meter telescope. So just 30 meters. And you might have read that at some point. They actually want to build that on Hawaii, on Mount, what is it, Mount K, always forget the name of the highest mountain up there. And they wanted to start to construct that actually last year, but there's lots of troubles going on with the natives there. They don't want to have another telescope on top of the mountain. So I think this October there were some first negotiations between the local government and the telescope consortium to build that. But anyway, so it was always the question, who is the first to set ground for the new telescope? So because of that, it's the Europeans. So we already started to build that one. So what have we to do with that? So Austria was for a long time not part of ESO and joined in 2008. Well, if you join this kind of organization, you have to put down a lot of money, something like, I think it's just the entrance fee is something like 35 million euro, and then you have to pay every year in order to use these facilities. And in this, when we actually negotiated the terms for Austria joining ESO, that was actually negotiated that there should be an Austrian scientific contribution, which was called at that time Mathematical Algorithms and Software for the E-ELT Adaptive Optics. That was a project that we did in Linz, the volume about 2.5 million euro. And so we started to work on that even before there was the final decision to build the E-ELT. Just that you get an idea how it looks like. Well, this is the Stephansdom, so the biggest church in Austria. So, and compared, that would be the VLT, and that is the ELT. So it's rather big. It's rather big, but it's actually, compared to the large-scale buildings that we have, it's not so big at all. So the pyramids are still bigger. So that's That's okay. So in order to do all the stuff, so we formed a so-called Austrian Adaptive Optics team. That's about 15, 16 people. They changed a little bit, so, and they come from 3 institutes. So that's the one, the Johan Radon Institute, then from my university institute, and then we have a company that's also part of the team. Just a few words. So the Industrial Mathematics Institute is a typical university institute. That's my institute, so we have about 10 applied mathematicians working there. So we work in particular inverse problems, that's the center, regularization theory, shape optimization, medical imaging, signal processing, and of course we do industrial projects. RICAM is a little bit on a larger scale, so we have, so as I said, it's a research institute of the Austrian Academy of Sciences, so there are no really ties to the university, which is quite nice up to some extent. So we are about 50, I think at the moment, 60 mathematicians working there, mainly postdocs. So postdocs stay there in average for, well, they can stay up to 6 years. So usually they never stay 6 years because they are quite often so good that they get calls to different professorships or different positions before the 6 years are over. So we are doing their basic research, again, inverse problems as a focus there, analysis and numerics of PDEs, symbolic computation plays an important role, optimization, imaging, and mathematical methods in life sciences and also industrial projects. So Math Consult is sort of a cash cow, so there we actually sell mathematics. So they do develop mathematical methods and software, in particular for automotive industry, steel production, metallurgy, finance, and there it's about 25 mathematicians, physicists, and computer scientists. So this is, so I always call that's the applied math cluster at Linz that we have there, which is, at least for Austria, it's pretty big. Okay, so now let's start a little bit with the background, what we are doing here. Well, if you have an optical system, if you have an imaging system, well, you have actually the original object that you have at your image, and you never get actually the true object back here. What you get is, well, you view it through an optical system, and mathematically, it means you have the original object is convolved with the point spread function, and that's here what you see. So for a telescope, if you take out the atmosphere, so if you would put a telescope if you would consider a telescope without atmosphere, so you shoot it into the sky, and the point spread function would be quite simple. You take the characteristic function of the telescope, that's a donut, and you take the Fourier transform, the absolute value squared, that's the point spread function. So you see here the point spread function of the very large telescope with 8 meters diameter, you see it. That's the one. And of the ELT, you have 40 meters, and you see the difference, of course. This one is much more spiky, and of course, what you would like to have here is, you would like to have here a point spread function which acts like a delta distribution. So you really need a very narrow peak for the point spread function, and that's actually the only reason why you build large telescopes. The larger the telescope, the more the point spread function actually approximates a delta distribution. That's why you do that. It's, however, not that easy. You have between, if you have an earthbound telescope on the Earth, you have in between the stars and the telescope, there is the atmosphere. And in the atmosphere, you have things like the jet stream and other things that move the air around. So you have turbulences in there. And if you have that, the turbulence actually comes into computation. Here it comes into this exponential term here, this phi. It's related to the turbulence. So you have the characteristic function of the telescope, you multiply it with this exponential, then you take the Fourier transform, absolute value squared. Well, and when you look at what you get without correction, just the PSF with atmosphere, you don't see a peak anymore. The peak is totally gone in the noise caused by the turbulence. And it's actually, you can actually show the bigger the telescope, the more pronounced this effect is going to be. So, and adaptive optics is a device that actually corrects for this imaging quality loss. So if you correct with adaptive optics system, you still see the peak here. This is one point, I mean, you would like to correct. It would be nice if you could correct once for all, but you can't because the atmosphere is moving, the turbulence actually is changing, and they are changing it's changing actually on a quite small scale. So there's this assumption of a frozen atmosphere, and they say, at least the atmosphere scientists say, well, the atmosphere stays frozen for about 2 milliseconds. So if you do a correction, you have to redo the correction every 2 milliseconds. And if you take an astronomical picture, it's usually, to take this picture, it takes between 10 to 30 minutes to take the pictures, because the object that you're imaging, they are so faint, so you have to collect all the light that you get. So you can imagine how often you have to correct there. So which means in this sense that the point spread function changes all the time. So you have to find something to correct that. Okay, and that's an adaptive optics system. So this is actually the simplest adaptive optics system that you actually could imagine. That's single conjugate adaptive optics. What you have is, well, the star is so far away that the incoming wave is a plane wave. So the wavefronts are plane waves. It's like you think you drop a stone in the water here at the American coast, and let's say we do it in New York, and then you look what's actually going to be happening in Amsterdam. So the waves that are coming in from that stone will be just parallel, right? So if you drop the stones, of course, it will be circles, but when they are coming to Europe, it's just plane waves that are arriving. Okay, so then they enter the atmosphere, and in the atmosphere, due to the turbulence, actually what happens is that the travel times change. So the wavefronts are not flat anymore, they got somehow crumpled. So they look like a crumpled sheet of paper. So then the idea that they had in the 60s, early 70s, I think, was quite easy. Well, a deformable mirror, a mirror that has not a flat shape, actually does exactly the same. So the idea was, well, you try to reconstruct the shape of the incoming wavefront. Now you deform this deformable mirror in the same way that is actually, this shape change is actually corrected. Well, and if you do that, the outgoing waves will be plane waves again. And the picture that you get will be sharp. So here's the system, that's how it looks in principle. So you have the telescope, primary mirror, secondary mirror, light goes to the tilt mirror, here's the deformable mirror, then most of the light goes to the imaging device, but you have a beam splitter here, part of the light goes to the wavefront sensor, then you do your computations here, the computations tell you how to deform the mirror, and so on. So adaptive optics is a hardware-based, real-time deblurring device. And one inverse problem, one of the first one, would be the computation of the right mirror deformation from the wavefront measurements of the incoming waves. So as I said, we have speed requirements. As the turbulence of the atmosphere changes rapidly, so in the in the best case actually, the reconstruction, each reconstruction must be finished in computation, or must be done in about 500 times per second. And that for not only for 30 minutes, but you do it the whole night because you do lots of observations every night. Okay, so here we have just a nice movie that actually shows that again. So we have this guide star here that sends out the waves. And here that's the effect of the atmosphere. Of course, it should be plane wave, the original object, the blurred object without correction. Then you do the adaptive optics system. You take a reference star, a bright star as reference object. You do some computations. Then that's the mirror. So you have to deform this mirror. Now you did it. And well, the outgoing wave is now corrected. It's a plane wave again. And the picture that you get is sharp. That looks nice. Come on. Yeah, just the turbulence above the telescope, that's something that looks like that. So you have, actually it's air moving over the telescope, and the air has different temperatures. That's what happens. And if you would actually know the wind speed up in the atmosphere, things would be easier, because more or less it's actually just a distribution moving over the telescope. Okay, so what is the different goals and different types of adaptive optics systems? Well, what you always need is a bright guide star. You need a bright star that you actually could measure the wavefront of, because the objects that you're interested, like kind of sketch of a galaxy, they are not bright enough to act as guide stars to actually measure the incoming wavefront. So you need actually an object which is close to this object that you would like to image, that acts as a guide star, and then you do the computation and you do the mirror deformation. You get the highest imaging quality in direction of the guide star. But the idea is, well, every object which is close enough still gets a good imaging quality. So that was actually the first adaptive optics system that has been in use. Then the idea was to use tomography-based systems for the correction. And here you have actually several guide stars around the object that you are looking at or that you are interested in. And so you do first an atmospheric tomography. Based on this data, you try to reconstruct the turbulence in the atmosphere. And well, then you have one deformable mirror, and this one deformable mirror is actually put or deformed in that way that you get the highest imaging quality right at the object that you like to look at. So that's the tomography systems. Well, then they came up with Multi Conjugate Adaptive Optics system, where you again do tomography of the atmosphere, but then you use several deformable mirror, each conjugated to a different height. So each conjugates for different part of the incoming wavefronts. And by doing so, you can actually get a high imaging quality in a big area. So you can image several objects at the same time. So several astronomers can actually observe different objects, which is actually quite interesting because so for the E-ELT, it's actually projected that the cost for one night, observation for one night, is about of 200,000 euro. So if scientists can observe several things at the same time, that of course would make a big advantage. Yeah, so said that all, so we have here uniform imaging quality within the field of view. Okay, and let's start with the first point here. That's the easier one, wavefront reconstruction, single conjugate adaptive optics. So the point is you have the waves coming in and you would like to reconstruct the wavefronts, and there's actually no imaging device or no instrument that would actually directly get you the shape of the incoming wavefront. So you have to use a wavefront sensor, and one typical wavefront sensor, the easiest one, is the so-called Schack-Hartmann sensor, and it actually works as follows. You have a square of several small lenslets. For the E-ELT, it's planned actually to have a square of 84 times 84 lenslets, and then you have the incoming wavefront. Well, if the incoming wavefront is really plain, so this wavefront falls onto this area of lenslets, and then you have this imaging device behind that. What you get actually, if you have a plain wavefront, is you get this time 4x4 and 4x4 array picture of the guide star that you're actually looking at, and this is totally irregular. So this tells you actually everything you have a plane wavefront. Now, if you have a tilted wavefront or a crumpled wavefront here, well, this picture, you still get pictures of the stars, but it's not regular anymore. And the deviation from the regular imaging tells you something about the average gradient of the incoming local wavefront. So the model, or one model of this wavefront sensor, is what you actually measure here is averaged over the subaperture. That would be the size of the small lenslet. You actually get the gradients here. So the simplest question would be, how do you actually, giving this data, how do you reconstruct the incoming wavefront? Well, and if you do your math, or if you took your Calculus 1 course, that's of course really easy if everything is one-dimensional. What you have to find is you have to integrate more or less a wavefront. You have the derivative, well, and that's actually the equation. Well, you can solve that, of course. You can calculate that. It's so this data at point xi plus 1, that's phi xi plus 1 minus phi xi. And, well, if you do the reconstruction as follows, just phi of 0 is 0, and then you simply sum up your wavefronts and you add the data here. And if you then shift it to 0, because the mean value of a wavefront is 0, then you have a reconstruction. That's, of course, everything is easy in one dimension, and two dimensions actually getting always a little bit more complicated. And this is mainly, in this case, related to the well, first we have not a regular square here, we have a donut. So there's some data is not there, so you have to adapt that. You have areas where you don't have data at all. So, but still you can get a similar algorithm which more or less sums up the data in a right way, more or less integrates the data, and get then the reconstruction. So that would be a reconstruction for 8-meter telescope, 84 times 84, and then that would be the correction, so the residual wavefront, so you get almost perfect correction. So what is the point here? What they did before at the ELT, at the VLT, what they're still doing at the VLT is doing a simple matrix vector reconstruction. So they set up the system matrix that maps the sensor measurement, maps the wavefronts to the sensor measurement, and then they simply invert this matrix. And if you do that on a 20-core machine, it actually takes 8 milliseconds to do the inversion here. There are several other variants of different algorithms there. So you go down up to 190 microseconds. So with our algorithm, so we actually did some cumulative algorithm that actually sums it up, and also did some clever domain decomposition in order to split the parts of the domain in the right size. So we can actually go down to 61 microseconds. So we just recalculated that at one time for ESO. Say, well, of course, we could actually simply take an iPhone and do the calculations for the VLT, where they have a large computer system at the moment, and we could do that with the iPhone. Of course, the problem would be not the iPhone, the problem would be to get the data in and out, so in the right time. But I didn't actually tell you about that. It's as we are really working in this 2 milliseconds regime, so we really can't do anything at once because everything really takes time. So the deformation of the mirror takes about 1 to 2 milliseconds. Reading out the data needs something like 1 to 2 milliseconds. So there is always a time shift that we have in the control, that we have to take into account in the control of the whole thing. But I'm not talking about that today. Okay, so for us that was the first big success in 2012 when this algorithm did run for the first time on a real telescope that's in Las Palmas in the Canary Islands on the Roque de los Muchachos. It's really a nice mountain up there, so you see a lot of stuff up there. And so the University of Durham in England actually did the test there, and the main point, you don't see much here. What you should actually take home with is that it's more or less the quality is, I mean, the seeing conditions were bad, otherwise you would have something a line like here. But the main point is that our algorithm did actually deliver the same quality than the old ones and was much, much faster. Okay, so then to atmospheric tomography. I said we have 2 atmospheric tomography systems that we actually consider. The first one would be Multi Conjugate Adaptive Optics, although it's the second one here. So we have several reference stars. For the ELT, there will be 6 reference guide stars that actually produce the reference incoming wavefronts. And we have 3 deformable mirror for the correction of the turbulence in the atmosphere. And that will give then a large field of view with good quality. And actually the TMT will have a similar system with 2 mirrors instead of 3. And then, which is really a new approach is multi-object adaptive optics. So you do again the same atmospheric imaging, so you do a reconstruction of the turbulence here, but what you then have actually, you have for each direction that you're interested in, you have a separate mirror. So you can actually observe up to 20, 25 objects at the same time. So this is the absolutely new system that has never been actually on SCAO, what they would put actually on the ELT. Okay, just a few words to the standard approach again. What is usually being done? First step is discretization of the atmosphere into a finite number of layers. So we always take here a layered approach. So we do not consider the atmosphere as a volume, as a turbulent volume. One reason for that is that, well, actually, if you would do so, we simply have not enough data to reconstruct the volume. So this is one point. The other point, which is, of course, much more important, is there's actually in the atmosphere, there are certain areas where there is turbulence and other areas there's no turbulence at all. So nothing happens. So like jet stream, there's lots of turbulence. Above ground, there's a lot of turbulence. And then there's a lot of areas where nothing happens. So having a layered approach for the atmosphere is quite good. If you do so, then you set up a system matrix that maps the sensor measurements to the mirror commands. So the system matrix here, you have the dimension of the wavefront sensors squared, then times the number of wavefront sensors times the dimension of the deformable mirror. So actuator position squared and the number of DMs. TMT, that would be 35,000 times around 8,000. E-ELT, 60,000 times 10,000. If you do standard computations, you solve systems for PDEs or whatever, so finite elements, you would say it's not big. But we have to solve these systems. They are full systems. They are not sparse. We have to solve them in 2 milliseconds. That's the challenge here. Yeah, so if you do it like that, just have the matrix there. Well, as I said, you have a high computational cost. And well, what is actually bad is whenever things change, you need to compute, you need to set up a new matrix, a new matrix for each guide star configuration. And also, I will tell you a little bit later, we'll go into that. Well, you measure 10 to 30 minutes. Well, in 10 to 30 minutes, actually the Earth does not stop. It actually moves. So which means the matrix that you're considered here, that is the right one. After 5 minutes, 2 minutes is not the right matrix anymore. So you have to recompute it. So this is, of course, very costly. So if you want to do some speed ups, you could do Fourier basis speed ups or whatever, then you need to transform it to different bases. And well, you have several subproblems hidden in here. And if you put everything into this matrix A, you cannot use anymore the specific properties of the subproblems. And I will show you that a little bit later. Okay, so our approach was try to solve the problem sequentially in a very efficient way. So first, reconstruct the incoming wavefronts from the Schack-Hartmann wavefront sensor measurements. And of course, we came to this approach because our wavefront sensor reconstructor is so fast. So we thought, okay, it costs no time at all, so we get this one for free. Then use the reconstructed wavefronts to reconstruct the turbulence layers. That's the second step. And then compute the optimal mirror shapes from the reconstructed atmosphere. And we found out also this part can be done in a very, very fast way. So in many cases, it's simply a projection of the reconstructed atmosphere to the mirrors. So we are left to find nice ways of reconstructing the wavefronts for reconstruct the turbulence layers from the wavefronts. And so this would be actually a 3-step solver, 2-step solver where we would actually combine step 1 and 2. Okay, and as I said, I mean, this can only be successful if all the subproblems can be solved extremely fast. Yeah, advantages, of course, the high flexibility. If the guide star configuration changed, you don't need to do much. You don't need to compute new matrices, optimization direction, and which directions you actually would like to see to have the best imaging quality. Also, that can be included into this approach in a very easy way. You can use the specific properties of the subproblems, and we totally get rid of matrix vector multiplication. So we don't need them anymore. So no pre-computations are needed in this case. So that would be this classical 3-step approach. So that's how the measurements look like. So that's the gradients, more or less the average gradients of the wavefronts. So you actually for each millisecond you have this is the data for one wavefront sensor measurements. You have that times 6, and even for these 2 images you get 1 incoming wavefronts. Then you do out of these 6 incoming wavefronts in different directions, you reconstruct the different atmospheric layers in the atmosphere. Standard approaches, what they do is they assume they have 9 layers, 9 turbulent layers in the atmosphere. And this is not just an assumption. What they usually do is every day they send up a balloon into the atmosphere in order to check if they are still okay with the location of the layers. We actually know that quite well. And then finally, if you have have done the reconstruction of the atmosphere, you get to compute the shape of the deformable mirrors. And if you compare that then to the incoming screen in that direction, you come to a residual, which means this is always almost zero, so you have an almost perfect correction. Okay, so tomography problem, just a short mathematical description. As I said, we have a layered atmosphere, so we assume that the atmosphere, the turbulences are just located in certain heights, and that the turbulences actually could be modeled as a 2D, just a plain 2D object here. So, and well, if you look in different directions, so you have different guide stars, what you can see is, well, you see that one here, a little bit higher up there, a little bit higher up there. So the higher you actually go, the bigger actually the area that you have to reconstruct. And if you assume that you have geometric propagation, well, a simple model here would be, well, the data that you measure down here is simply summing up the shifted turbulence or the influence of the shifted turbulence in the different directions here. So if you would now assume that you have an infinite number of layers, then of course this sum here would be an integral, and what you would get here is a simple Radon transform. So this is more or less kind of a discretization of the Radon transform. So the task is, in order to reconstruct that, is reconstruct these turbulence layers from the measurements. Okay, so just some notations. So we have assumed that we have L turbulent layers. We do notate that we do write them down as phi up L, and then we collect everything in this vector of layers. So each of these phi's is still a function. Standard inner products, L2 inner products. We also did some work on Sobolev norms as inner products, which gives some better results, but take longer in reconstruction. This omega t here, that will be the area of the telescope down here. The omega L's, that's the layers that can be reconstructed, and you see actually as we have an opening angle, so what can be reconstructed is actually just this area, just this intersection of these circles. Okay, and the guide star directions, that's this alpha G. Okay, so nice and easy. The problem is the number of stars, the number of bright stars on the sky. So you need the guide stars need to be bright enough, and well, if you just count all the bright guide stars, you actually get about a coverage of sky of about 5%, which is of course not nice, and many of the interesting objects are not located close to these guide stars. So what are they doing? Well, they actually create their own guide stars, so-called laser guide stars. So around the telescope, you assemble something like, for the ELT, it's 6 powerful lasers, and these actually shoot the beams into the atmosphere. And at a height of about 90 kilometers, there is a sodium layer, and in the sodium layers, these lasers actually excite electrons, and by doing so, they actually create an artificial star. So, and you can actually, this artificial star is bright enough, so you can actually use that as a guide star. That's good, isn't it? However, there's no free lunch. Well, I had a free lunch today. So anyway, the problem is, well, if you have the light from a real star, it comes from infinity and travels once through the atmosphere. Well, the light from the laser, actually, it travels through the atmosphere. It's actually always, I mean, every turbulent layers actually change the direction in this a little bit, then it creates the guide star, and then it goes back. So, but it goes back the same way. So you lose some information if you do so. So you lose the information. What is wrong actually in your measurements here is that the average of the derivatives of the incoming wavefront is actually wrong. You can forget it, so you cannot deal with that. So what's the strategy? Well, we use a combination of laser guide stars and natural guide stars. And we actually use the natural guide stars only in order to get this information on the first derivative right. So in order to do so, you can actually use much fainter stars. So you can use much more stars. So this is a solution. So what you do is you remove the wrong laser guide star tip tilt. So that's the first derivative in x and y. You're doing that by doing this operation here. Well, and then you estimate the correct tip tilt from the natural guide star measurements. So there's a way around that. Then what else do we have? Well, the natural guide stars, so they are created at 90 kilometers. But compared to the infinite dimension that a star is, this is still, like waving a flashlight. So it's not, so the light is not traveling in a cone, it's not traveling in a cylinder, but it's actually traveling in a cone. So you can correct for that. So actually the areas here getting bigger the more you go actually towards the telescope. You can correct that with a simple factor here. No problem at all. That's really easy. But then there's another problem, so-called spot elongation. So what actually happens is the following. So this layer, the sodium layer, is in 90 kilometers, and it has it's actually not a thin layer. It's about several kilometers in, so that actually it's several kilometers thick. So you do not create a point source, but you create actually an elongated point source. So if you're actually standing directly at the laser position and look up, what you see is actually just a point source. Everything fine. But it's actually like that. So you have the laser somewhere is here at one point, and then you have one of the apertures where you measure that's here. So you are looking up there, and what you see is not anymore a point, but it's this elongated point source. So, and you actually, well, here you actually do know exactly where you have an idea where the center is. Here you don't. So you have to do something in order to find the center of this elongated source. And there's different approaches for the TMT and the ELT. So ELT has the lasers around the mirror outside. TMT has them inside. So if you have them inside, then of course you're always wherever you're much closer to the point source. Outside, you're farther away. If you are, however, inside, the problem that actually the laser beams influence each other, that happens more often than when you're outside. Again, no free lunch. So what you can do is you have a noise model in there where actually you say, well, you transform that with a matrix C here, you take white noise, and then that's actually what you get as a noise model for here, and you can actually use this a priori information for the reconstruction. Okay, so what I now want to tell you a little bit about is the periodized atmospheric tomography operator. So that's a kind of an analysis. I want to go through that a little bit fast. I hope, maybe not too fast, but that's actually the point. If you're not so interested in the formulas, you can actually have the nap. So what are we doing here? What we wanted to do is we really wanted to compute an analytic decomposition of the operator in terms of singular functions and singular values. And well, due to the relatively complicated geometry, so doing that directly on the geometry that we have in hand wasn't, at least not yet possible. So what we did is that we considered a square here, and in this square we actually put in both all the wavefronts and all the layers and all heights. So it's a reasonably big one. So it's about for the ELT that would be about I think 51 or something like that meters in size. And that's where we actually would like to reconstruct. Okay, and then we consider the atmospheric tomography operator as an operator mapping from L2 spaces in L2 spaces. So that's the layer space here. That's the wavefront space. And what we then use is the Fourier approach. So we use the Fourier basis in order to decompose these incoming wavefronts and the layers. And if you do that, well, what you actually find is, well, we have here the Fourier series for all the incoming wavefronts, the Fourier series for all the incoming layers, and then we collect for each JK, so for each basis function, for each Fourier basis function, we actually collect the coefficients of each of these functions. So that would be something like here for the ELT, these vectors for each jk, that would be a vector with 6 elements. For each jk here for the layers, would be with 9 elements, or maybe if you have more layers, up to 20 elements. And then you define some small system matrix, AJK, BJK, so defined here. And then these matrix AJK has these entries here, so you evaluate the basis function to the exponential function at this point, multiply with this scaling parameter here, and then you assemble these matrices. BJK is just applying AJK to the Hermitian of AJK. So this is a G by G matrix. G is, just to remind you, it's 6. That would be 6 by 9. So, and well, if you do that, you can actually write the action of the adjoint and of the direct operator in a very easy way by simply collecting all the coefficients of your, that would be here, wavefronts, and then you have these vectors here. That's, as I said, it's 1.6, it's a vector with 6 elements, and you multiply that with the matrix B, JK, and you have to do that with all the coefficients, and the same for applying A to these, to your basis function. You simply have to apply the small matrix AJK to the vector of the vector of the coefficients given here. So that's just small matrix vector multiplications that you have to do for each of that. And of course, I mean, you can do that in computations. That would help. It goes quite fast. But the main point is the following proposition that you get, namely that the singular values of the operator A are, of course, given by the singular values of the matrices AJK. So in order to compute the singular values of a full operator that acts between infinite dimensional spaces, what you have to do is you have to compute singular values of small matrices. So that makes, of course, things much more easy. Well, and if you have these eigenvalues, you can also do, well, the singular values of AJK are the singular values of A, and the eigenvalues of A star are given by the eigenvalues of this symmetric or Hermitian matrix BJK. Okay, so, and the eigenfunctions, the associated eigenfunctions are as follows. So we have the eigenvalue of the matrix BJK, has an associated eigenvector. Then if we multiply this eigenvector here with the basis function UJK, then actually we have an associated eigenfunction to the operator A star. And well, we get the eigen or the singular functions for the operator AJK, or for the operator A, which is not symmetric. We simply get that, well, that's this function here, that's the one singular functions, and we get TJK, the other singular function, simply by applying the Hermitian of this matrix AJK. So this, everything is very cheap. So then we have a standard decomposition as what we would have for compact operators. So we can really write that down in terms of a singular value decomposition or an eigenvalue decomposition. So, and of course, if you know, well, if you did your course functional analysis with compact operators, of course, you know where you get the inverse or the generalized inverse simply by dividing by the square root of the eigenfunctions, of the eigenvectors. So that's how you actually would invert. Of course, you never do that in practice because the eigenvalues are small and actually everything would blow up. However, there's some really astonishing things happening in here. So the first thing that I realized at some point was, well, you would expect that the atmospheric tomography operator is kind of a tomography operator. It's a limited angle problem. And for limited angle problems, you know, they are exceptionally ill-posed. So, and they're of course also compact. However, the atmospheric tomography operator A is not compact. And this is simply a result coming from the fact that you actually go from the full atmosphere just to a layered atmosphere. So that actually summing up functions is not a compact. It's not an operation that actually makes things compact. Summing up a finite number of functions doesn't make an operator, doesn't make the operation compact. that is one thing that was interesting. The second thing I found even more interesting, and that was actually the following result. Well, we have a direction of, you have the direction of the guide stars. Well, if these numbers here, so that's the x component of the guide star direction, times the height of the layers divided by this scaling factors, and the same for the y component. If these numbers for all L and for all G's are rational numbers, which is kind of strange. However, if this is the case, then actually the generalized inverse is continuous. This is even more interesting because you would think you have a limited angle tomography problem, severely ill-posed, and now you can show there is actually a continuous inverse. And why is that? This is actually a simple, quite nice result. So we have an exponential function, more or less we have the matrix that we actually assembled, these AJKs, they just have exponential functions in there. So these factors that actually enter into these exponential functions, the coefficients, so it would be e to the power I, pi, and then something like this values. So if it's a rational number in there, so and you increase k, so you compute it for different k, all the natural numbers, so you get from some point on, the matrices, they repeat themselves. So you get the same matrices. But you only get that result when these factors here are rational numbers. If they're real numbers, real numbers, not rational numbers, then actually all the matrices will be different and you will get tons of different eigenvalues. So in this case, you have an infinite dimensional eigenspace, but you only have a finite number of eigenvalues. So, and the remark then, the point of course is that in this case, the inversion is stable, which is somehow nice. On the other hand, what you see in the computation is, well, it is continuously invertible, but it's still ill-conditioned. So it's still, you have a smallest eigenvalue, but the smallest eigenvalue is still not really large, as we will see there. And so actually Andreas Neubauer, he really did a computation then for a very easy example showing that, well, if G and L is 2, so that's the very easiest case, which is the very easiest non-trivial case. And he showed that even when that condition is violated, you really get eigenvalues that converge to 0. So this is a really a nice result. Okay, so just some numerical validations. So that's I just wanted to see that we are doing the same with our periodic operator. So that's some incoming wavefronts. And if you look at the application of the operator A star, that's the Fourier setting implementation. That's a validated implementation that we had before. You get, in principle, the right thing. So the differences is really, really small. And if you look at the singular values of the operator A, you see a nice picture here. So you have something like, that's here the minimal singular values. Well, you have in the center here, that would be the coefficient for a constant function. You have a very high value, and then the numbers are getting small. And well, that's actually the lines where you get larger null spaces for your operator. And here you see the largest singular values in each direction for each pair of JK. Of course, in the center we have the largest values. But you see actually quite nice in which directions we have the guide stars. So that's kind of easy to see here. Okay, so what is nice is also the distribution of the singular values. This is actually a setting that will be run at the telescope directly. So the geometry and so is the right one. So you see that actually most of the eigenvalues are large. You only have very few eigenvalues which are small. Actually, if you say looking for the number of eigenvalues which are larger than 10 to the power minus 4, that's 99% of them are larger than this number here. So they're really actually big. So that's the numbers of eigenvalues that we gather form the null space. So it's actually, you can do a nice inversion based on that. Okay, so for last minutes, just some results on reconstructors for atmospheric tomography. As I said, I'm not going into Kaczmarz. you might have heard about Kaczmarz. In Kaczmarz, you actually try to minimize the residual in each direction separately, and then you sample them all. Kaczmarz was a nice, it's RT for tomography. It's a nice actually method that we actually used. Just a few words to the wavelet-based method. Why we are using wavelet? Well, we use wavelets to represent the turbulence layers, and the main point is wavelets have very nice approximative properties, so you need only just a small number of coefficients for representing the wave fronts, and the discrete wavelet transform is O of n operation, so you can do that very, very fast. So, and our wavelet of choice was almost WC3 here. And again, we have to solve this equation here. So that's the atmospheric tomography operator, and that's the measurements, that's what we would like to reconstruct. And in this approach, we do everything in a Bayesian framework, which means we consider all these variables here, the measurements and the layers and the noise, as random variables. And the question is then, given a noisy measurement, what phi here occurs with highest probability? Answer is, if you take a maximum a posteriori estimate, you have to minimize this functional. So this is the prior here. You have the prior for the turbulence of the atmosphere, and that's the noise covariance matrix here. So we use the discretization here using wavelets. So we go from layers to coefficients for layers. So then the forward operator goes from A to A tilde. And the nice thing that we actually used here is that this penalty term here, using the Bernstein-Jackson inequalities, so we can evaluate that by applying a diagonal matrix on the coefficients of the wavelets. So this matrix here is diagonal, okay? And yeah, so in order to solve that, we have to solve this Tikhonov system here. So that's the diagonal operator in wavelet basis. That is the atmospheric tomography operator in wavelet basis. This one is diagonal, as I said. That's the wavelet coefficients. But however, in the wavelet basis, this is not sparse. Unfortunately, it's not sparse. However, if you decompose the atmospheric tomography operator in a bilinear base, then this matrix here is sparse. So the idea here is, well, we are doing the following. We actually plug in the wavelet and the inverse wavelet transform, which just takes O of n operations here, and where we do evaluate the diagonal operator for the covariance matrix here in the wavelet basis, and we do the application of the atmospheric tomography operator in the bilinear basis, and switch between these two settings just using the fast wavelet transform. And then, well, you need to do we can actually use the conjugate gradient methods for finding the solution. You have to look a little bit for the right preconditioner. So we constructed a really nice preconditioner for this method. It's frequency dependent, and then we get a nice solution. So just some simulations here. Well, that's this configuration for the ELT, the right thing that we have to do. So we have 32 meters, 6 laser guide stars, 3 natural guide stars, 3 deformable mirror, and this is actually all simulated in Octopus, which is a simulation tool, an end-to-end simulation tool at ESO. And so just the speed results, what I did before with matrix vector multiplication, it actually took them 92 milliseconds for one reconstruction. So with our finite element wavelet method, so we are down to 3 milliseconds, where you can actually see, and this is actually on a standard computer, standard workstation, so nothing specific. But that's what I want to have. And the one question was, should we actually try harder in order to go down to 2 milliseconds? Then we actually thought, well, they will actually finishing constructing this thing by its first slide will be 2024. We just wait. So we just take the computers then. They can do that, not a problem at all. For Kaczmarz, actually, we need less than 1 milliseconds at the moment. But at that, for some systems, we have some problems with achieving the right quality here. Then you have to actually compute the optimal mirror deformation with respect to the reconstructed atmosphere. So this is another optimization problem here formulated in a continuous setting again. So you have the atmosphere, you have reconstructed, and you would like to find the right shape of the mirrors. And well, depending on how you discretize this approach here, how you discretize this integral here, this optimization problem, you get different results. And we found actually if you take a 4x4 Gaussian quadrature rule for approximating this integral, we get the best results. So the highest imaging quality inside here, and also by reducing the computational time by down to 36% of what we had before. Just some outlook, I'm not going into that. If you have done all that, you can actually, after the correction, you can reconstruct, based on the data that you have, you can reconstruct the point spread function in each direction. So you can use that for many things. So astronomers like to look at the reconstructed point spread function in order to evaluate the imaging quality that they can actually expect in their images. But you could also do, of course, you could say, okay, we have an image, we have a point spread function, let's do a deconvolution. So, and we are currently working on nice algorithms for really trying to getting better images based on a deconvolution based on the reconstruction of the point spread function. What else do we have to do? Well, then there's the first things, what we have to do is the nasty reality. So we have to deal with nasty reality in different settings. The first one is, I showed you the telescope. You have the primary mirror, and then you have the secondary mirror, which is on top of that. So the secondary mirror actually doesn't float above the telescope. There is a mechanical structure that connects the secondary mirror with the primary mirror. However, that actually means, well, you don't see the full aperture here of the telescope. You don't get the full image, but there are missing data. That's what I call spiders. So that actually disconnects your area. So if the areas would be connected, that would be much nicer. And this is actually just not a line. It's actually like a space like that. So you have somehow to find nice places and nice algorithms to put these data in a right way together in order for the wavefront reconstruction in particular, that these reconstructed wavefronts in each of these segments fit together. Then you also have to take care of, there's something, at first wind has an effect. The wind actually shakes the telescope. That's one thing you have to take into account. You have to correct for that. The other thing is, well, the telescope moves. So it really moves because it has to follow the object in order to, it always has to have the object in the center. So also you have vibrations there that affect the alignment of sensors and wavefront sensors and mirrors. So you have to take care of that. You also work on optimization of the reconstruction layer profiles. Question, which layers would be best suited for the reconstruction? And how many layers do you really need to get a good reconstruction? And then the last point that I just want to drop on you is a totally new project that we are hopefully going to start soon. Gaia. Gaia is a satellite from ESO, and that's actually, I think it has been launched 2 years ago, and it collects the largest database of our galaxy. So it takes information from all the stars in our galaxy, I hope from millions of stars in the galaxy, and what people at the astronomy department of University of Vienna would like to find out is, based on these data, how is actually the interstellar matter, that is just dust in space, how is that actually distributed? If they find out, if they get a good idea how that is distributed, that gives you information on how our universe actually expands and what else. So that's something to probably get some nature publications or whatever. So the point what you actually get here is, again, it's a tomography. But again, it's even more difficult because, well, it would be nice. So that's where the Earth is. That's where Gaia is, the satellite collecting the data. But however, at some point, of course, Gaia moves. But with respect to the whole universe, it is simply stuck in one point, namely there. So we just get projections in one direction. So it's like you just get one projection on your CT data and you would like to reconstruct. It's, of course, totally hopeless. what you have to put in that is lots of additional information on the distribution of dust in space and how there are lots of astrophysical assumptions in order to do that. And the idea is this is also a project that it's going for 10 years. In 10 years, some guy at ESA actually will push a button, and then all the data will be distributed. And those who actually have the fastest algorithm to really go through the data, that's millions of data that you have, and assemble the data, reconstruct the data, that will be the guys that actually will have the publications in the high-ranked journals. And the goal of the project is that's us. So, okay, that's what I wanted to tell you. And I hope it was not too mathematical or not too little mathematics in there, whatever is your flavor, just some, some publications. And, well, thank you. So if there are no questions, that just means I explained everything so perfect and everybody understood everything. It's just a 2D function. It's a function. It's a function that's just living in a plane, and it's you have it's. I mean, the modeling would be so you have a stochastic approach for modeling it. So it's a van Karman statistics, or it follows either van Karman or Kolmogorov statistics. That's what you actually apply there. So the modeling is quite simple. What you do is you have certain parameters in there. So you have an atmospheric parameter which tells you the strength of the turbulence. This is some input, and then what you actually do is in the simulation, how you simulate is you actually take you create random numbers in a square area, and then you know from van Karman or from Kolmogorov statistics that it actually behaves like it's actually in a Sobolev space with exponent 11/6 exactly, and you multiply with that function in order to get a statistics or an atmosphere which actually follows the statistics of that actually Kolmogorov or van Karman predicted. Now the PSF is actually, I mean, based on the turbulence in the atmosphere, the PSF actually changes. Yeah. Yeah.
But to follow up on that question, that's your regularizer model, right? That's your prior. So when you talk about the solar.
It's both. It's actually both. You use it. You use it first, I mean, to describe the atmosphere. So that's somehow verified that the atmosphere behaves like that. So in atmospheric sciences, that's somehow they accept it. Well, and of course, you also use that as a prior for your reconstruction. You say, okay, you would like to reconstruct an atmosphere that really follows the statistics of the atmosphere. Yeah. 11/6. Yes, it's less than 2. Yeah.
It's not. You don't have very strong. It's not a very strong.
It's not very strong, but it helps actually. If you don't use it, then actually you get worse reconstruction results. So for the catch mesh reconstructor, we don't use it, so the quality drops a bit. So it really helps to have that in there.
The other thing is for the construction. You mentioned just started on that right now. So you use these squares, calcium, not Poisson, because you've got all these very low light and very fast.
So we are using a Gaussian, not a Poisson. It is actually, they say, well, in principle, it is of course a Poisson, but there's actually they have this. If they collect long enough the light, then it's Gaussian. So.
But you need to do this at every frame, right?
Right. Yeah. That's actually the reason why you need bright guide stars. I mean, if you have much fainter guide stars, then it would be Poisson distributed, and then you would have to do something else. So it's something like a photon flux. You have to have. Well, sometimes you have 10,000 photons coming in per frame, and that's what you need somehow. If you go down to 500 photons per frame, then it's getting getting worse. Yeah. This affects the reconstruction quality. And because then also the readout noise from the sensor actually is sometimes larger than actually the information that you get. As WC3, we use WC3. So that worked. So it's a nice balance of being, so I mean, if you want to use the Bernstein-Jackson inequalities, then you need to have a wavelet that is smooth enough to have this inequality work, this equivalence between the norms working. But on the other hand, the smoother the wavelet, the slower the wavelet transform is going to be. L2. It's all L2. L1 is too slow. Yeah, it's too slow yet. We would like to do L1 or maybe even, yeah, L1 or let's say LP, we would like to do that. We tried that. It works. It gives some better results, but on the other hand, you need so much more time for the reconstruction, for the minimizing of the functionals that it's actually just not working. Not yet. 10 years is a long time. Yeah. That's true.
You're not deploying this tomorrow. You got time, audience.
Yeah. The point is always, I mean, I didn't like that when I first learned that. I mean, so with such a project, they are using techniques which are available today. So which means in 10 years, it's supposed to be ready. So it's old. Yeah. So, but we hope, I mean, the computer system will be one of the last things probably that will be installed. But so that's not a problem. And we really hope to can be there on the project with our instruments for quite a long time. So I mean, so at the moment we have these projects going on for the instruments for the ELT, and that is also scheduled up to 2024.
Thank you for a great talk, and you can follow up with.
Yeah.